Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to talk about something called tangent planes, but I want to start off and just kind of give you a little taste of something that involves partial differential equations a ton. So next year, if any of you are still at Stargate or honestly in college, you might take this course called Differential Equations. And more specifically, it would be ordinary differential equations. So ODEs are what we call those. And they're just differential equations that use like the derivative that you saw in a Calc 1 course. There's also something called partial differential equations, which are like this thing down here. And they just use partial derivatives. So a lot of times after a Calc 3 class, you would take you might double up in like linear algebra and differential equations. This linear algebra course isn't really like using a ton of this or anything like that. And if you really want to challenge yourself, you might try to take a partial differential equations course. But it's probably a good idea to take this differential equations first. But just to kind of show you what these sort of look like. So this is actually a very famous one. This is called the Laplace equation. And when I've taught differential equations in the past, like this ODE course, at the end of it, I do a little unit on partial differential equations, just to kind of get students like some exposure. But just to show you guys right now, because we're talking about partials, there's technically a Laplace equation in like higher dimensions too, and you literally just add this second order partial like for the next variable and for the next variable however many times you want. But a lot of solving differential equations is coming up with this, and to come up with these equations can be really hard. But here I just want you to see that this function actually solves this equation. So if we were going to take the partial of u with respect to x, right, the sine y part is constant, so we literally just have e to the x sine y. Then partial of u with respect to y is e to the x is constant, right? And then the derivative of sine is cosine, so we just get e to the x cosine. And we also need the second order partials, so we're going to need like uxx. And so here you just would get the exact same thing because e to the x is not going to change. But then when you do uyy, right, you're going to get negative e to the x cosine, whoops, not cosine, sine y, just the derivative of cosine there. And so then if you take these and you just plug them in, you can see that it actually solves it. So if you do e to the x sine y minus e to the x sine y, so this is, the uxx, uyy, actually cancels out and gives you 0. Yay. So this is, not what we do in differential equations a lot. A lot of times we have to just craft it, but I just wanted you to see kind of like what a differential equation looks like. And I just went to Wikipedia and I just Googled partial differential equations just to show you. There's a ton of these things. So hopefully some of this notation now makes sense, like this kind of stuff. This is a fourth order differential equation. So there's like, partial of u with respect to z 4 times there. I don't know what many of these are. There's all sorts of different things. I know this one well. This one well. This one I've used. But there's a ton here. And the list really just goes on and on and on. But there's a whole slew of this stuff in physics and engineering. You can see like the topics that it applies to over here. A lot of these like fluid dynamics, that's very common to have like anything with motion because, when we're talking about derivatives, there's some sort of motion involved. So ton of this stuff. You really can't get away from them in like higher order applied math and science problems. So that's just a very short taste of what those look like. The plan for today, though, is to really just talk about something called tangent planes. And tangent planes are fairly straightforward, but they use partial derivatives, so I wanted you to see them. This thing, right, is just point-slope equation, right? You can just, have a point and then some sort of slope from there, and you can get a line, right? So if we change some variables around, right, this is actually still, like, I would call it point slope, but it's just point slope in the z plane, right? And it would still work the same way. The point is y1, z1, and the slope is still the m. And you can extend this structure in math really, really easily. So if you think about this, right, this would now be like the dimension up analog to a line, which is a plane, right? And it's a plane that goes through x1, y1, z1, and it has like slopes, m1 and m2. But basically what that means is, like, if you have, your xyz axis, you've got like some slope 1, we'll call that m1, and then maybe like m2 is over here, and then those kind of define direction vectors for the plane, and then you can create like a plane that includes those, like this. So that's basically what this thing is telling you to do. If we use that idea of like the plane kind of equation structure, we can just pop in f with respect to x and f with respect to y at the point, like x, y, z, and that would instead give me a tangent plane, right? So it would be like if you have some sort of surface, and you have like a point, right? It's like you've got, some curve that's in line with, say, like the x direction, and then you've got some curve that's in line with like the y direction. And what we're basically going to do here is we're going to take tangent lines. This is like f with respect to y at the point, and then another tangent line here, f with respect to x, and then let those be like my direction vectors for the plane. And then the rest of it is just the same, like put the point, this point in here. So it's really just using like the structure of a plane that we know, and then just adding the extra piece of the slopes of the like tangent lines at the point. And that would give us a tangent plane. So this is kind of like what I'm talking about here in a picture. So you have like some sort of surface, and this red point over here, you can have like a plane that comes in and touches it at like one spot right there. So to do that, you're going to need to find these two partials. So this is my function, f with respect to x is going to be 4x, f with respect to y is going to be 2y, and then the point is 1, 1, 3. And so I can just go and plug in, to this equation now. Z minus 1 equals I'll put that in a second. Oh, wait. Actually, I'm going to back up a second. So I need the partial evaluated at the point. So I need f with respect to x valued at 1, 1, which is going to be 4. And then f with respect to y evaluated at 1, 1, which is 2. So that's the things that I'm going to plug into here and here. So now I can do it. So z minus 1 equals 4 times x minus, this is not a 1. This is a 3. It's this, z value. And then x minus 1 plus 2 times y minus 1. And And technically, that is an equation of this plane, but, it's kind of good to multiply some of this stuff out. So we get 4x minus 4 plus 2y minus 2. And then I'm going to add the 3 over. So negative 4 minus 2 is negative 6. Plus 3 is negative 3. And that's it. Pretty straightforward. The idea is honestly probably the most important thing here. So, basically we're just using the notion of the slope of the tangent lines, but we're using it, twice, popping it into what we know as like an equation of a plane. And then that plane will be forced to be tangent now to the point in question. Another use of this stuff is something called linear approximation. So when you get to like harder courses, a lot of engineering again, it gets hard to sometimes work with the messy function. Now this one's actually a fairly easy function, but if it's really, really complicated, what we do is we actually create these tangent planes, and then we use those as an approximation for what this looks like, but only near the point. And close to the point is going to be good, and the further away it would get worse, right? The idea is like, if this was the surface, I can like zoom in and zoom in, zoom in right by the point, and like it'll start to look like the surface is, linear really by that point. Like if I zoom in far enough, then the surface is going to literally start to look like a plane. It's like if you ever go to like, Desmos and you have a quadratic and you just like zoom in on like any part of it, right? And then you blow that picture up, then it's going to look like maybe something like that. And then you could like zoom in again, and then it will look even more like a line, right? And this just keeps going and keeps going. You can just do the same thing with a surface. So it's kind of just a lazy shortcut, but honestly, like mathematically, this acts the same way as this if you're close to that point. And close is all relative. If you were, at different types of engineering firms, they're going to have like different levels and margins of error that they will let you kind of be within that point. Sometimes you might need to be really, really, really close if you're like building something where, people are going to be walking on it, like a bridge or something. You got to be like super safe. So it's totally dependent on the problem, but everyone would rather work with this over this if they could. And that's the idea of linear approximation. Basically take a gross thing and find this tangent plane and just work with the tangent plane near the point. So I just want to do one of those. So if we were going to find the linear approximation of this function at this point, so this is like a weird 4D surface, okay? A 4D point, right? And I want to know what plane basically acts the way this does at that point. So I just need f with respect to x, f with respect to y, and f with respect to z, all right? And so if we do x, you have like a chain rule, right? So you're going to have like a 1/2 in front, and then you're going to have everything inside here. And then you're going to now raise it to the negative 1/2. You're going to drop power by 1, right? And then chain rule, you got to multiply by the derivative of the inside, which is, for the x part, it's just going to be the 2x. So then the 2's cancel, and so you would get like x over the square root of x squared plus y squared plus z squared. And honestly, like all of them have that sort of structure. So I'm just going to put the other ones up. So you're going to have y over square root x squared plus y squared plus z squared. And then you're going to have z over square root of x squared plus y squared plus z squared. And then you do need to evaluate it at the points, right? So if you do f of x at 3, 2, 6. You can trust me because I did it before, but you should get 3, 7. You just plug it in, you get 3 7ths. If you do that for y, you would get 2 7ths. And last but not least, if you do it for z, you get 6 7ths. So then you have technically everything you need for the plane. You can just go and, so I'm going to use, I'm going to let w equal f of x, y, z. So basically w is my last variable. So w minus 7, right, would equal 3 7ths times x minus 3 plus 2 7ths times y minus 2, and then plus 6 7ths z minus 6. And I'm not going to bother multiplying it all out, but this is like a computer could have a much easier time understanding this thing over this thing. And so if you're near that point, you can just find the tangent plane in order to approximate this thing and figure out what properties of it are and analyze behaviors of it and stuff like that. All right, just want to do one more problem, which I think is just a good one that's from the book. But basically, you don't know the equation of a tangent plane to some surface at a point, and you don't have the equation of the surface, but you know that the curve that's parametrically defined as R1 and R2 here, that they both lie in that surface. And from that, you can get an equation of the tangent plane. So just kind of like always, I would recommend you try to think about how to do this. I'm just going to jump into it, but if I was you, I'd pause and kind of ponder and think about how you might go about doing that. But without further ado, I'm going to do it. So I think I'm going to kind of try to draw just roughly what this might look like. So again, just think like you have some sort of surface, okay? And you got some curve, like this one is, I'm going to say R1, and then you get some other curve like this, let's say is R2. Then you have some point that they both go through. Okay, this is my point P. And what I basically can do is take, tangent vectors to both curves at that point, and that'll represent direction vectors, and then I can pop those in, and I can get an equation of the tangent plane. So that's going to be what I'm going to do. So I got to start with derivatives. So I need R1 prime, and R1 prime is 3 and then minus 2t minus 4 plus 2t. R2 prime is 2u, 6u squared, and 2. And I also need to know, what t gets me this and what u gets me this point, because they're not necessarily the same. So I think the easiest one for t is, let's say, I need 2 plus 3t to equal 2, right? So t equals 0. I can just see that this 2 plus 3t needs to be 2. So t is 0. And then I'm going to say 2u plus 1 needs to equal 3. So u equals 1. And I'm just getting that out of the last one right here. So then I can evaluate R1 prime at 0, right? And I get 3, 0, negative 4. And then R2, this is supposed to be prime at 1 is, let's see, it's 2, 6, 2. And so those are these two vectors right here. And technically you could do cross product and get like an equation of the tangent plane that, so you could do a cross product. Let me go to like this one. You could do a cross product and you could get like these like normal vectors, right, out of the cross product, and that would give you like a vector that points like out of the plane. And then you could use this form and simplify it. But honestly, I think it's the easiest way is vector form. So I'm going to just do vector form. So it's still an equation of a plane. You got x, y, z. And then the point that it needs to happen at is 2, 1, 3. And then I'm just going to use a as like a scalar. 3, 0, negative 4. And then plus b times 2, 6, 2. And that's perfectly okay. The other option is use cross product, and you can get a normal vector from that. So you could do like ijk, and then you could put in, where was it? 3, 0, negative 4, 2, 6, 2. And this would give you a vector that basically needs to go into this kind of structure here. And then you could simplify it out. But you can also get that form by just using like a system of equations and like solving for a and b and like plugging them in that way too. But this is perfectly good.